So this is also being broadcasted in YouTube, and it is also being broadcasted in Facebook. So if you are not in the class, or if you miss the seat somehow, you were logged out and you don't want to, you want to come back and something, so you can always use the YouTube link to join this. Okay, so here we go. I'll just put the link here. Right. Okay, so let's talk about some interesting mathematics. This is the session for a math Olympiad that is coming up in the month of July. So if you have not registered for it yet, you should definitely go ahead and register for it in our website. It's at chinta.com/Bose. You can do this at the end of today's class. If you want to join the Maths Olympiad program that we conduct, you can also do that there. If you are referred to us by someone, your school or your organization, you can talk to them for a coupon code that will help, a scholarship code in some sense, to help get a better pricing. All right. All right. So let's talk about some mathematics today. This is a very interesting topic from Combinatorics. So if you have, how many of you have played chess before? If you have played chess before, then can you say if you have seen this before or not? Okay, some of you have played chess before. Okay, that's great. Excellent. So I personally, I love chess a lot. So that's there. Okay, great. Now, this is a game of something called non-attacking rooks. So maybe I can change the color of the pen just to see what's going on. So there are certain pieces called rooks on the chessboard. And suppose you have a chessboard like this, like the one that I have drawn in the picture. So you have a chessboard like that. And you have two rooks, one white rook and one black rook on the chessboard. So instead of white and black, we will do red and green. That would be better for us. We have two rooks on the board. So maybe one of them is here. I'll use, okay, maybe I can use a more darker shade of green. Okay, maybe I can use black. Let's use black. So this black triangle is a rook on this chessboard. This black triangle is a rook on this chessboard. So the rook can move horizontally like this. So it can move left and right, and it can move up and down. That's how the rooks work. So it's a piece on the chessboard, and it can move sideways. Of course, it can move sideways, and it can move up and down. It can move sideways as well. So if I draw the black rook where I have drawn, if I draw the black rook where I have drawn it, the arrows tell you its zone of attack. It's very important. Zone of attack. The arrows tell you its zone of attack, which means that's the black region is where it can attack some other piece. It can eat it. It can attack some other piece or it can eat it. Okay. Now, okay, maybe I can mute this. This is wasting my time. Okay, and I will do one more thing. Just give me a second. Okay, here you go. All right, so now there is another rook on the board. There is another rook on the board, which is probably here. So I'm drawing this other rook in red. Now let's draw the zone of attack of this red rook. The red rook's zone of attack is this one. So you have left and right, you have up and down. You have left and right, you have up and down. So now notice that the black rook is not in the zone of attack of the red one. The black rook is not in the zone of attack of the red one. The black rook is not in the zone of attack of the red one. And the red rook is not in the zone of attack of the black one. Sorry, you should be able to hear me clearly. Is if you are can any of you hear me clearly? Hello, Aryan, are you able to hear me clearly? For example, okay. So if you can not hear me, then please raise your volume in your device. Okay. So notice that this black rook is not in the zone of attack of the red one, and the red rook is not in the zone of attack of the black one. So this is what we want. This is the situation that we are interested in. So we want to put them on a chessboard. Look at here, the instructions are coming up. So put them on a chessboard such that they do not attack each other. They do not attack each other. So this is one such configuration. This is one such configuration where the rooks won't be able to attack each other. The rooks won't be able to attack each other. It's a very special scenario. We want to know how many ways can you do this? How many ways can you put two non-attacking rooks on the board? How many ways can you put two non-attacking rooks on the board such that of course non-attacking means by default they won't attack each other? That's the question. Okay, so this is a kind of a complicated question. It is a challenging problem. So this is just our motivating problem. We will be using it to do a much more interesting problem, a much more sort of a challenging set of ideas to reach this problem. So we will not solve this problem right away. You can think about this problem as a challenge problem, and if you can do it, send me an answer. Okay, but to understand how to do this problem, let's start with a very beautiful strategy of counting things. So this is another problem to tell you exactly how to do it. Okay, so this is a much easier problem. You should be able to do this. All of you should be able to do this. This problem is known as the three towns problem. So there are three towns, A, B, and C, in Wonderland. So A, B, C. There are three towns in a place called Wonderland. It's given that 6 roads go from A to B. There are 6 roads that go from A to B. And there are 4 roads that go from B to C. 6 roads go from A to B, and 4 roads go from B to C. The question is, in how many ways can one drive from A to C? So those who have seen this type of problems before, you can do this right away. But let me show a picture of this once so that we can analyze what is exactly happening in this problem. We are just using this problem to learn a much bigger strategy, a much more powerful strategy of counting things. And that is the multiplication principle, as some of you have pointed out. Multiplication principle. So how does this work? You see, there are 6 roads from A to B. So I will give names to these 6 roads. I'll give names to these 6 roads. So this is R1, R2, R3, R4, R5, R6. There are 6 roads from A to B. And then there are 4 roads from B to C. So let's give them names as well. T1, T2, T3, and T4. So as many of you have pointed out, there are 24 ways to go from A to C. So that's what you want to do. You want to go from A to C. You want to go from A to C. So the only way you can go from A to C is you have to first, step 1, you have to first go from A to B, and then you have to do step 2. And can anyone tell me what is the step 2? What is the second step? First you go from A to B. That's your step 1. And then what is your step 2? Exactly. As Ritesh, Aryan, and others are saying, this is very good. The step 2 is B to C. Now notice the most important word in this particular description that I gave you. What is the most important word here? The most important word is and. This is the most important word. And means multiplication. You will see in a moment why that is true. But even if you are a student of computer science, if you are doing informatics Olympiad, if you are doing maybe some sort of a programming, you directly know what I'm talking about. Step 1 and step 2 means you have to multiply the number of ways of doing step 1 and with the number of ways of doing step 2. So let's see why that is true. So how many choices do we have for step 1? How many choices do we have for step 1? So there are precisely 6 choices, right? R1, R2, R3, R4. There are 4 here, and R5, R6. These are the 6 choices for step 1. Okay, great. Now let's look at the number of choices for step 2. And as many of you have rightly pointed out, there are 4 choices for step 2. 4 choices. So there are 4 choices for step 2. Let's look into that. You have T1, T2, T3, T4. You have T1, T2, T3, T4. If your first choice is R1, the second choice could be T1, the second choice could be T2, the second choice could be T3, the second choice could be T4, right? Okay, now let's do R2 Again, for R2, we have the same thing, T1, T2, T3, and T4 for the second choice. Okay, so if you want to build a code, if you wanted to build a code that tells your friend which path you have taken, then it would be something like this, R1, T1. Maybe you say, okay, R1, R1, T1 is the code for your journey. What does that mean? Well, that means that you first take road 1 and then you take T2, T1, that is the road from B to C. Another code will be R1T2. Another code will be R1T3. Another code will be R1T4. Well, what do I mean by a code? Well, a code is the number of ways, is a description of the path that you are actually taking. It's the description of the path that you are actually taking. So how many codes can you make? So you can make 24 codes. Why? Because there are 6 choices for the first spot. There are 6 choices for the first spot. And for each of the 6 choices for the first spot, you have 4 choices for the second spot. So in total, you have 6 times 4, 24 choices. Now you might wonder that, okay, this seems very easy. Why is he spending so much time on it? Because what we are learning here will be useful in much more complicated problems. So we have to stop here, wait a little bit, think a little bit, and then do this. Okay. So I'll give you the second principle that we will need. The second principle. And that is the addition principle. So let's move on to the next problem. That we add another town to this picture. We add another town to this picture. So all of you can notice this. This other town is B. Now you have another town, a second town, and this second town is the town D. Here you go. You add another town. Now there are ways for going from A to D. How many ways are there? Can anyone tell me, looking at the picture? How many roads are going from A to D? Okay, there are, how many ways are exactly? Many of you are giving me the right answer. So this was R1, R2, R3, R4, R5, R6, and this was T1, T2, T3, T4. Now we have new roads. So there are 3 ways to go from A to D, which is, let's call them S1, S2, S3. And there are 2 ways to go from D to C. D to C. Let's call them M1 and M2. Okay. Now so a new town called D was built. A new town called D has been built. D. Several new roads were created. So these are the new roads. 3 roads from A to D and 2 roads from D to C. Okay. How many roads are there now to go from A to C? That's the question. Right now, how many roads are there to go from A to C? So you want to still go from A to C. How many ways are there to go from A to C? Now, this is a very sort of a simple example of something called addition principle. So you can write this down in your notebook. Addition principle. This is one of the most useful tools of counting or something called combinatorics. Okay. So what is the addition principle? There are 2 different ways to go from A to C. Okay, can anyone tell me what are these two different ways to go from A to C? What are these two different ways to go from A to C? There are two different type of paths that you can follow. There are two different types of paths that you can follow. Ah, Shauradip is right. Excellent. Shauradip is saying, okay, there can be two cases. Case one, you can go from A to B to C, and case two, you can go from A to B to C. Okay, A to B to C and A to D to C. Now, can anyone tell me, can these two cases happen together? Can case one and case two happen simultaneously? Is it possible? It's not possible that case one and case two happens simultaneously, right? Okay, so what we do here is we write the word or. This is very, very important. Or means, in fact, to make it a little bit clear, what I'll do is I'll not even write or, I will write XOR. This is a notation borrowed from computer science. This is a notation borrowed from computer science. Can all of you hear me? Hello? Okay. So what is XOR? If you have done computer science before, or if you are into programming, in some sort of programming, you already know this. XOR is something called exclusive OR, which means that case 1 and case 2 cannot happen together. It's case 1 or it's case 2, but not both of them together, right? So this means addition. This means addition. Why? Because what you do is you compute all the possible cases for case 1, which we already know how to do it. We already have seen this. There are 6 ways for A to B, and there are 4 ways from for B to C. 6 ways, 4 ways. So total 24 ways are there to go from A to C via B. This is just case 1. And then you have case 2. You have case 2, which is you go from A to D and then you go from D to C. So how many choices are there for A to D? For A to D, there are 3 choices. For A to D, there are 3 choices. For D to C, there are 2 choices. So you again multiply, because A to D and D to C, A to D and D to C. So there are 3 times 2, 6 cases. And there are 6 times 4, 24 cases. So in total, now how many cases do you have? Exactly, this is 24. You take either one of these 24 roots, or you take one of these 6 roots. You take one of these 24 roots, or you take one of these 6 roots. So you have in total 24 plus 6, 30 routes. So in this problem, first you used multiplication principle for each of the cases, and then you used addition principle. Okay, so I would strongly recommend you to switch off the video, please, because this is being broadcasted in YouTube. So if you do not switch off the video, whatever is happening in your home, everyone is seeing it. It's not very nice. Thank you. Okay. So we have total 30 cases, right? Like this. Okay. We have total 30 cases. So we understand what is multiplication principle. We understand what is addition principle. Now, let's use them together to talk about this problem of teacups, saucers, and teaspoons. It's a very simple problem. So you are in a tea party store. You are in a tea party store. There are 5 different teacups. There are 5 different teacups in the store. Okay. So there are 5 different teacups in the store. And there are 3 different saucers. There are 3 different saucers. Saucers means these are plates. Okay. Saucers are plates. There are 5 different teacups, and there are 3 different saucers, and there are 4 different teaspoons. 4 different teaspoons. What do you want to do? You want to buy 2 items with different names. You want to buy 2 items with different names. Okay. The question is, how many ways can you do this? How many ways can you do this? So if you know the answer, you can put it in a private message. You don't have to put it with everyone, like, so others can try. So there are 5 different teacups, 3 different saucers, and 4 different teaspoons. You want to buy 2 of these items with different names. You want to buy 2 of these items with different names. How many ways are there to do this? Okay. So as you are doing this problem, let me remind you that the Bose Maths Olympiad is coming up, and this is the page for this. You can register yourself there. It's coming up in the month of July. So I'll give you a link to register so that you can, I'll put the link in the chat. It's chinta.com/Bose. You can register it there. If you are recommended to this seminars by your in a school or your family friend or something, they can also provide you with an access code. They can also provide you with an access code. So you can give the access code and join this Maths Olympiad. We will have these sort of seminars every week. These are open seminars. But if you want, you can also join the actual Maths Olympiad program, which is, of course, happening 3 times a week. There are one-to-one classes, group classes. Again, whoever has recommended you should have some sort of a scholarship code that will bring down the cost of this program. So you should definitely talk to them. Okay. So both of these are, everything is happening online, of course. So you can talk to them and understand what's going on. And if you are watching this, you can in YouTube, you can also subscribe to the YouTube channel just to make sure that you get notified for the upcoming videos that we have. So we have many more videos that that come up. So I'll just, every week there are different videos coming up actually. So you have this is the YouTube channel. You can go there and subscribe. and you can go to chinta.com. Oops, I think this is going privately, not cool. Okay, so this is the YouTube channel, and this is the chinta.com/Bose for the Maths Olympiad registration. You should definitely check that out as well. Okay. All right, coming back to this problem. So this is a very powerful problem, friends. I mean, this is a very interesting. Okay, so let me go back a little bit. Oops, sorry. Yeah, teacup saucer problem. So this one is interesting for a multiple reasons. And one of the first reasons it is interesting is because this involves something called selection. Selection. You see, this problem was handled by one of the mathematicians from antiquity called Holayud. He was a Indian mathematician who was studying music. An Indian mathematician from 9th or 10th century, I think. He was studying music and he was selecting different notes of music to create something called chanda. And so while he was doing that, he found a beautiful mathematics behind it. So he created something called Meru Prasthar. And about 600 years later, an European mathematician called Pascal found the same thing, and the world knows this as Pascal's triangle. But of course, in India, it was known about 600 years before this. Pascal's triangle came up, and it was known as Menu Prasthar, created by Halayut. So this actually is the starting point of the things that we are discussing today. Starting points in the sense we want to select two things out of three things. So what are the three things? We have broadly three objects: the teacups, the saucers, the teaspoons. So let me write that. And this will involve, maybe I can write it here. This will involve the addition principle. So you have teacups, you have saucers, and you have spoons. So you want to select two objects out of these three objects. So I want to introduce a notation here, okay? I will call it 3 choose 2. I'll call it 3 choose 2, okay? So what is 3 choose 2? It is simply the number of ways of selecting two objects out of three objects. It's the number of ways of selecting two objects out of three objects. Okay. You see, what can you do? You can either, so this is case 1. So can anyone tell me what is the case 1? If you wanted to choose 2 out of 3 things, these 3 things, what could be the first way of doing it? If you wanted to choose 2 out of these 3 things, what could be the first way of doing that? So you have to tell me what 2 things you want to select. Out of cups, saucers, and spoons. So cups, saucers, and spoons. If you wanted to select, okay, so Ritesh is right, excellent. The case 1 could be You choose cup and saucer. Very nice. What could be the case 2? Case 2 could be, so if the case 1 is cups and saucers, case 2 could be cups and spoons, okay? And what else could happen? Case 3 is spoons and saucers, right? So if you think about it, there are only these 3 cases if you want to select 2 objects out of 3 objects. Cups and saucers, cups and spoons, spoons and saucers. So this 3 choose 2, we say that's equal to 3. Why? Because there are 3 ways of doing this. There are 3 ways of selecting 2 objects out of 3 objects. There are 3 ways of selecting. You can write this down actually, because if you don't understand it right away, you can think about it, what I'm saying. There are 3 ways of selecting 2 objects out of 3 objects, 3 different objects. Let's call this distinct objects. So we say this entire sentence can be coded into this: 3 choose 2 is equal to 3. Instead of writing this big sentence, we can write 3 choose 2 equals to 3. Okay. All right. So now your challenge, and you have to do this on your own, your challenge is to use the addition principle. So each of these cases will be distinct. So you can write XOR here. So use the multiplication principle to find the number of possibilities of each of these cases, and Shauradip is putting out the answer already. So number of possibilities of each of these cases, and then add them up to get the final answer. Okay, great. So we will be stopping out here, and I will see you next time, hopefully with more beautiful problems. In the meantime, keep on solving great problems and stay well. Okay, bye all of you.